All right. Hello, hope you're doing well. And this video will cover kind of the other half of titration reactions. And what we're going to look at is a acetic acid or N-acetic acid titration, which is a weak acid, with sodium hydroxide, which is a strong base. So we have a weak acid plus a strong base. And in this titration, as we'll see, the net reaction will essentially look like something like this. Like you have your weak acid, HA, strong base, OH minus, turns into A minus in water. Okay, and I can break that down in a second, exactly how we got that. But for now, let's just kind of look at this. And what happens when you're kind of graphing the pH, it starts off a little bit higher than your strong acid. So maybe, not close to zero, but a little bit higher in terms of your weak acid pH that you're starting at. And then when you add the base, it also kind of has this little inflection where it kind of goes up and levels out. And then you have your equivalence point, and then it levels out at the top again. So a couple differences. One similarity is your equivalence point is here. But before the equivalence point, so essentially this region here we call the buffer region, because we have created a buffer. We're going to have HA and A minus in that region in the solution, which again creates a buffer. So that's why as we're adding the strong base, this is staying fairly level in terms of the pH. Equivalence point key difference here is that the pH is actually basic. So a lot of times people associate equivalence point with being neutral, but that's only if you're mixing two strong things. The weak acid and the strong base equivalence point is greater than 7, and we'll see how that works in a few minutes. So otherwise, let's jump into these calculations where we're adding different amounts of the base, like we did with the acid, or the strong acid and strong base titration. So we are starting with 100 mils of 0.4 molar acetic acid. That's going to be, oops, not the one I wanted, 0.1 liters times 0.4 is 0.04 moles of acetic acid, which we can again just call HA if we want to make it a little bit shorter. And at this point, since we're titrating with 0.2 molar NaOH, we have added 0.1 liters. That's going to be 0.1 liters times 0.2 equals 0.02 moles of NaOH, which again is just the same amount of OH because we want to kind of break it down into that species, the net species. Okay, so to review, like we did previously, write the net reaction, do your stoichiometry table, see what's left over. All right, so net reaction here. Okay, so if we imagine starting with acetic acid, and then again, if you're writing like kind of NaOH, this would break up into sodium plus OH minus, right? And the sodium is going to end up canceling with another sodium on this side from your total ionic reaction. So the thing to remember is that a weak acid, you don't want to dissociate it and don't write H plus in something else. You want to keep it kind of undissociated. And that's why we end up with a net reaction that looks like this, which again, we can just abbreviate as this. And I kind of like this way because then again, any weak acid titration I'm doing, I'm like, oh, I know it's going to be this net reaction. I don't need to worry about which weak acid it is. Okay. And also, when you do a titration, you only titrate with a strong base. So you would never start with a weak acid and then add a weak base. It just is not done. So you're never going to have a base that's different than hydroxide here, I guess being the point. So write down the moles like we did before, do our stoichiometry table. This is going to be 0 here. We're doing a titration, so we're just starting with the weak acid. We don't have any A-. That's important. Okay, so like before, this is a stoichiometry or before and after, initial, final, whatever way you want to think about it. Just subtracting the smaller number, right? So we can kind of look at these and say, oh, that OH is smaller. I'm going to subtract that. Here, we definitely have to add it to the right side, to the A-, right? Water we don't need to keep track of, but don't forget to add that over here. That's important. So what we end up with is some of the weak acid left over, the hydroxide's used up, and we've produced some of the conjugate base. So what do we have now? Well, in this scenario, this is the second scenario, you don't have H plus or OH left over, so it's not that one. We do have HA and A-, which, if we recall, is a buffer, and we can use the kind of the more easy ways to use that Henderson-Hasselbalch equation. Okay, so buffer solution and plug it into here. Okay, so if you look up on the acid chart, the Ka, or sorry, the pKa of acetic acid is 4.75. This is from our table. And then I can, again, easily do this in, or more easily just in moles without actually converting to molarity, because it's the same ratio. So again, if you remember that from the last video, or from the buffer video, mole ratio works fine in terms of the A- over HA. You don't want to convert to molarity. And this becomes 0 because the log of 1 is 0. So this is just the pH, or the pH is just the pKa, I should say. Okay, so I'll point this out up here. Again, we're basically right here in part A. We're like actually halfway to the equivalence point, right in the middle of the buffer region. And this specific point is called the half equivalence point. Half equivalence point, pH equals pKa. So what the half equivalence point means is that you've added exactly half your original moles of HA, you've added half of that of the hydroxide. And you're going to end up with equal amounts of HA and A-. So, end up with equal HA and A-. Okay. But again, you can end up in the buffer region at any point before the equivalence point. So really, it's the same problem. All right, at this kind of juncture, we've added 200 milliliters of our sodium hydroxide, and that's going to be 0.04 moles of the base. So if I do 0.2 liters times 0.2 molarity, that's 0.04 moles of NaOH, which would be the same number of moles of OH minus. Again, we're going to assume we're kind of starting from the beginning. There's no A- left over, or no A- produced. So what we see is that this is the equivalence point. We've added equal amounts of the base as the acid that we started with. So we go this and only have A- left over. So is it neutral because we're at the equivalence point? Again, this is a common misconception. Maybe on first kind of glance, you would say that, oh yeah, you've completely neutralized the acid with the base. It should be neutral. But because we have a weak acid and a strong base, what happens is that we end up creating the conjugate base of the weak acid. And so I'm going to write this down here. Equivalence point ends up being basic due to the presence of A minus, right? Which is a base. It's not just water like in a strong acid, strong base titration, which would be force neutral. It's water plus this weak base here. That's the key. This problem is kind of the longer one of the titration problems, because what we have left over is now we're in the third scenario here. So we have only a weak acid or only a weak base. And then in this case, we have to do a weak base equilibrium. So this now it becomes a problem of, oh, I have a weak base in the solution. Going back to chapter 7, this is that situation where we just have a weak base. Okay, so what we end up writing is the weak base plus water, and it always will end up being the opposite of the titration reaction. The one we just wrote, this is going to be opposite. This is going to be an equilibrium reaction because the K will be small. Keep in mind, if this reaction went basically all the way to the right, we had a very, very large K, driving the reaction to the product. So when we flip it around, this reaction will have a small K value. That's why we're doing equilibrium. So now we're going back to an ice table, right? So kind of one really important theme is like the opposite of an ice table is a stoichiometry table, because one reaction like partially reacts and the other reaction goes to completion. So that's kind of a good thing to, at least it's not always true, but at least for acid-base chemistry, that's essentially true. So because the K's are usually really big and really small. If you have a K close to 1, it would kind of be the same if you flipped it around. So I should clarify that. Okay, so when we do your ice table, one thing to keep in mind is you don't want to put 0.04 here, because we want to go back to molarity when we're doing the ice table, right? So let's figure that out. Concentration of A minus is 0.04 moles. Remember to divide by your total volume. So you're starting with 100 mils of the acetic acid, and at this point we've dropped in 200 mils of the base, so it should be a total of 0.3 liters, I should say, and that would give us 0.133, and then we can put that in here. These would be 0, and as we kind of remember from our stoichiometry part, now so what we're kind of assuming is that this is going to kind of react the other way a little bit, and again x should be small, so we can do our small x approximation. So when we solve for the K, remember this is going to be a KB, so we have to do that extra step of solving for the KB of the acetate ion, the conjugate base of acetic acid, and this is got a KB value of about 5.68 times 10 to the negative 10, and we're going to assume this is x squared over 0.133, doing our small x approximation. All right. So again, this is kind of a long problem. It's kind of 2 problems put together, your titration, and then just another weak base problem. So this is 8.69 times 10 to the negative 6, which remember is for a base, the X is hydroxide. So the POH, if I take the negative log of that, I get 5.06, and the pH is 8.94. Okay, again, just the normal steps to go from this to that, and then that to that. All right, this makes sense. This is a weak base, so it does have a basic pH. And again, that we just did the equivalence point. So we did one where we're before the equivalence point, that was a buffer region. We did at the equivalence point. Again, just to complete this, we're just going to go past the equivalence point and do one more part, and then we'll have done essentially every part of this kind of titration. So in part C, it gets easier as you get to this point too. So again, just kind of work on that equivalence point one. That's really the one that you want to get kind of familiar with and be able to do. If you can do that one, I think you'll be pretty confident with titration problems. So what happens with the 0.3 liters is that this is now 0.06 moles of OH. Again, I'll just kind of, you can verify that, but that's just easy polarity calculation. This is going to be 0. And so what happens now is that we use up the weak acid, right? We've gone past the equivalent moles needed. We've added more moles of hydroxide, dropped more base, got more funky. And so now we have this ending up, with our scenario, right? Moles of hydroxide, moles of A minus. Okay, so at first it might be a little bit weird, or like, well, what do? I have a strong base and I have this conjugate weak base. But again, this is taken care of in our little methodology, these things here, because what I have here is that if you have H plus or OH minus left over, that's just basically going to be how you find the pH, right? So what I wrote, like if you have H plus and HA, disregard the weak acid. If you have OH minus and A minus, disregard the weak base, right? As we've said before, a strong base and a weak base, the strong thing is going to dominate and determine the pH. Strong acid, weak acid, just take the strong acid. So we're going to ignore weak base and just use the hydroxide moles to find the pOH. So this is going to be 0.02 moles. At this point, we've added 300 mils, so that's 0.4 liters total. You could find the hydroxide concentration if you want, or just take the negative log. This is going to be 1.3 for our pOH, and our pH therefore is 12.7. So again, once you go past the equivalence point, because you have extra hydroxide, pH should be pretty high. So that makes sense. So there you have it. Again, you want to practice these, and kind of there's some good book problems that have you do similar things where you go through multiple parts of a titration. I kind of want to point out at this place that if you have a weak base titration, starting with a weak base and adding a strong acid, that is one other type, but essentially it's the same thing that we just did. And I think there are some book problems regarding this as well. So it would be like flipping the graph that we just drew. So it would basically go like this. So you're kind of inverting it. So you'd have, starting with a weak base, you'd start off at a pH that's above 7. And then you would create a buffer region. Okay, so if you want to think about like your net reaction, you would start with a weak base like A minus. You're going to add strong acid. Your net reaction kind of looks something like this, generally. So in your buffer region, again, you're going to have A minus and HA that are produced in the solution. Once you get to your equivalence point, imagine if you start off with 0.1 moles and 0.1 moles. Well, you're going to use those up. There's going to be 0, and then you're going to have 0.1 moles of your HA, your weak acid. So your equivalence point is going to be acidic, right? So it's going to be some kind of pH below 7. So weak base and a strong acid, the pH will end up below 7 at the equivalence point. But again, if you just use those steps that we talked about for any titration reaction, it'll work for this. It might be good to practice just in case. These aren't as common, but I think if you want to be fully prepared, you would want to at least see how these are done as well. And yeah, if you have any questions, send me an email or come to study hall. Happy to help. Good luck with all the practice problems and the studying. Talk to you later.